Hello everyone. So let us continue our study about for the topic of electrostatics with a new concept of Gauss Law. Before introducing the Gauss Law, let us just recall a few things which we would require while using this Gauss Law. In our earlier classes, we have discussed about flux. And we said that the flux is a scalar quantity phi, which is calculated by E dot A, right? And we also told that the flux entering a surface is positive, flux leaving a surface is negative, right? So now what does this has to do with the Gauss law? What Gauss law says is, see, consider a 3D closed object. Suppose let it be in this way. The shape is arbitrary. Let this has Q1, Q2, Q3 charges inside and Q4 charge outside. So, see, what do we tell about the electric field about here? We tell that the electric field here is equal to the electric field is due to by the superposition principle. We tell that the electric field at this point is equal to the effect of all the electric fields. And we tell the E net. Now, let us try to if we try to calculate the flux through this surface. See, this is a 3D surface, so it is a surface basically. We are having area vector this way. So, if we try to calculate the flux would be, considering this to be a very small area of dA magnitude, we say that the flux is equals to, see, the flux due to this small element E vector dot dA vector. So the total flux would be right. Note that this electric field is due to all the charges present. Now, according to Gauss law, this turns out to be that this flux, the net flux, is equal to this phi, which is the net flux through the surface, this is equal to Q enclosed. What is basically Q1 plus Q2 plus Q3? Those are the charges present inside the body. So the Gauss law says us that the net electric flux through a surface is equal to the charge enclosed inside it by epsilon naught. Now what does that mean? See, there are a few misconceptions which generally happen to occur. See, here the flux is equals to and So the surface integral of the electric field depends only on Q1, Q2 and Q3. So what if I say that I add another charge here, Q6. Okay. So in this case, flux changes because charge enclosed inside it changes. Also electric field changes because there is an inclusion of a new charge. But what if, suppose I do not include this Q6 charge inside, I include it somewhere here. Here I am speaking about the electric field at a point. Now in this case, phi does not change, but electric field changes. Why? Because see, electric field is due to the net effect of all the charges. Since there is a new charge present here, the electric field also changes accordingly, but still the surface integral would remain the same. So this is a point of confusion which we should avoid, that flux depends only on the charge enclosed, but the electric field which we use during calculating the flux is due to all the charges. Now there is one more scenario wherein I just relocate this charge. Initially it was here, now it is here. In this case also, phi does not change, but electric field changes. There are a few misconceptions about this topic which we generally have to take care about while answering any type of a question. So now, now a general question which occurs to our mind is, but what is the use of this Gauss law? Gauss law has been useful for us in many ways to find the flux through surfaces. See, consider a cube. Okay. And there is a charge Q present at the center. Now, let this be if someone asks, find out the flux through any one of the faces. So what do we say? See, if we think about it in a different way, let us there is also one face here and there is also one face back. If we keenly observe, we find that this charge is placed in a symmetrical way with respect to all the faces. Thus, see, suppose the flux through this face is phi 1, the flux through this face is phi 2, the flux through this surface is phi 3, the flux through the downward surface is phi 4, the flux through the backward one is phi 5, the flux through this backward one is phi 6. So by superposition thing, what do we say? The net flux through the cube is equal to right? But see, since all the faces are symmetrical with respect to the charge Q, we say that okay, so what, and thus it turns out that phi net is equal to 6 times phi of phase. Take any phase, the flux passing through that phase into 6 is equal to the net flux. Now by Gauss law we know that, see, since there is the charge enclosed in only Q, so the net flux will be equal to Q by epsilon naught. Thus we find out that flux through a phase is equal to, okay, so this way we solve this question. Now let us complicate this question a bit more. See, what if I say that now this is a cube and a charge is placed at this corner. Now I want to find out the flux through this phase. Now one may observe that, see, let this be phase 1, this 2, this 3, the backward one 4, the here one side 5 and the downward one 6. So we say that, see, the phases like 2, 3 and 4 are equivalent and phases 1, 5 and 6 are equivalent. So one way, and see, since the charge is here, the flux through because the field lines passing through this surface, this phase will be grazing them, and thus the electric field at this point will be, the electric field to the dot product of the area will be 0. Thus one may arrive at a misconception that the remaining phi 1, phi 5, phi 6, which is equal to 3 times phi 1, will be equal to the phi net. Yeah, obviously this is true, but in this case phi net is not equal to Q by epsilon naught. Why is it not equal? See, since it is at the corner, the charge is not totally enclosed. It is, some part of it is outside and some part of it is inside. So in this case, what do is, we try to make a figures in which the symmetry exists. So now we kind of extend this thing. Okay, so if you see that, it becomes in this way. So see, with the charge being at this center, so we are required to find out the flux through this surface, right? Now, how many surfaces are there? See, every surface is symmetrical with respect to this charge. So see, count the number of surfaces. 1, 2, 3, 4. 4 faces here into 6 sides of this bigger cube. So the total number of faces will be 24. Thus 24 times phi 1 will be equal to phi net. And now what is phi net? Phi net is equal to Q by epsilon naught. Why is it true here? Here it is true because in this case the charge is totally enclosed inside the figure. Thus, we say that phi 1 is equals to q by 24 epsilon naught. Right? Now I'll give you one more important formula which will be used in many of the problems to be solved next. So the question says, like, the formula is, suppose there is a charge q here and there is a ring here in such a way that this angle is alpha, this is also alpha. So see, when this charge is there will be field lines passing this way, right? So the flux through a ring phi is equal to one minus cos alpha. So this is a very important formula which will be deployed to solve any of our questions. So, like, the proof of it comes from this thing. Like, for whoever is interested, you can just go and search for solid angle, and there you will get the proof of this. Solid angle is basically, see, what do we say? We say that, like, if we take a paper is a 2D figure. Now the paper extends some angle here, and thus we call it angle. This angle is a 2D angle, theta. Now if you take a cone, the cone would be, like, in this 2D plane the angle is theta, but there will be some more space, like it will be taking proper amount of space, and that angle is basically known as solid angle, and the relation between solid angle and the complete angle is, if the 2D angle is cos theta, then the solid angle is equal to 2 pi times 1 minus cos theta. So basically, if there is a whole sphere, the 2D angle exerted, like, by the whole sphere made by a whole sphere is 2 pi. Sorry, okay. Okay, yeah, 2 pi times 1 minus cos theta. This is a formula which we are going to use now. Now let us use this formula and try to solve a question. We are given a cylinder . Okay, let this be phase 1, this lateral surface be phase 2, and this be phase 3. Given that there is a charge plus q at the center of the surface, also given that this length is L, this length is root 3L. Radius, basically, this length. So we are asked to find out the flux through cylinder, flux through phase 1, flux through phase 2, and flux through phase 3. So first of all, it's very clear that since the charge is on the phase 1, it will be generated, like, the electric field lines will pass parallelly to the phase, and thus the electric flux will be 0 because the angle between the area vector and the electric line is 90 degree. Thus cos theta becomes 0 and thus the flux is 0. So very clearly phi 1 is equal to 0. Now what about this phi of cylinder? Is it equal to q by epsilon naught? The answer is no, it is not. Again, why? Because the charge is not enclosed. See, whenever this kind of a situation arises, suppose you have a hemisphere having charge plus q here, and we are supposed to find out the flux rate. So what we do is we superimpose a similar hemisphere over it, and then let this be 1, let this be 2. We know that phi 1 is equals to phi 2, and phi 1 plus phi 2 is equals to phi net. So 2 times phi 2 is equals to phi net is equal to q by epsilon naught, because now the charge is completely enclosed. So we find out phi 2 is equals to q by 2 epsilon naught. In similar fashion, if we start here, we say that, see, this is the cylinder. I draw on this thing. Now this is plus q charge. Let this be 1, this be 2. Flux through first cylinder plus flux through second cylinder is equals to flux net, and flux 1 is equal to flux 2. So 2 times flux 2 will be equal to q by epsilon naught. Thus flux 2 is equal to q by 2 epsilon naught. Thus we found out that the flux through the cylinder is equals to q by 2 epsilon naught. So let us just write it over here. And flux 1 was 0. Now what next? See, we get to know that it's very difficult to find out the flux through the phase 2, because every time we have to take a strip, then find out the electric field, take the dot product area. Instead, what do we do here is very logical and very smart way of finding it out. See, let us first find out the flux through 3. Now for flux through 3, let us ignore all this stuff, and we know that there is a charge q here. There is this phase, which is a ring-like structure, right? This distance is root 3L. This distance is L. Let this distance, let the angle be alpha. So from here, what do we know? Tan alpha is equals to root 3, which implies alpha is equals to 60 degrees. So by the formula which we have written earlier, we say that the flux through 3 is equals to q by 2 epsilon naught times 1 minus cos 60 degree. This is equal to q by 4 epsilon naught, right? Because it becomes 1 minus half, so it is half. So q by 2 epsilon naught into 1 by 2 is q by 4 epsilon naught. Now here what comes is very interesting. See, the net flux, that is a phi of cylinder, is equals to phi 1 plus phi 2 plus phi 3. Now we know what is phi of cylinder. Phi of cylinder is q by 2 epsilon naught. Phi 1 is 0. We need to find out phi 2. Phi 3 is. So what does it mean? Thus, it turns out to be q by 4 epsilon naught. Just imagine, had we not had the Gauss law, it would have been very difficult to find out this flux. And if we don't know this thing, we would not been able to find this flux. Thus, Gauss law helps us a lot. Even like some or the other way, this finding out this flux is also related to Gauss law, but still it can be done without the Gauss law also. So this is the importance of Gauss law, and remember that whenever a question comes in such a manner where you have to find out the flux, try to use the Gauss law, because in most of the cases you will find that using Gauss law would help you in getting the answer. Now let me introduce you to the concept of cavity. See, consider a charge sphere. Okay, having uniform volume charge distribution rho. So before going to the cavity part, let us use the Gauss law in a few more situations. So how do we tell? Like, how do we find out what is the electric field at a distance small r from the center? This is a sphere, by the way. Okay, so for this, what do we do? See, let the electric field be E. Since the charge is uniformly distributed, we know that the electric field will be same at all the points. So, through Gauss law, we know that integral E dot dA is equals to the charge present inside. So, what is the charge present inside? Rho times dV by epsilon naught. Right? Because we don't know the amount of charge present inside. Now, consider this thing. What is the area vector? Area vector is in this direction, which is parallel to the electric field. So, this dot product is equal to E times dA, and since E is constant everywhere, so E times integral of dA is equals to integral of rho dV. See, even rho is constant, so rho is outside by epsilon naught. So what is electric field times integral of dA is 4 pi r square. This is equal to rho times, what is integral of volume? It is 4 by 3 pi r cube by epsilon naught. So 4 pi r square, 4 pi r square also. So electric field is equals to rho r by 3 epsilon naught. In vector form, we can write it as electric field is equal to rho times r vector by 3 epsilon naught. See, when is this electric field? In a solid charge sphere. This is when r is less than capital R. Now consider the situation where R is greater than capital R. In that case, this is R. Take a Gaussian surface here. So again, the electric field is same. So E times integral of dA would be equal to rho times integral of, so rho times integral of dV by epsilon naught. But remember, there the limits everywhere is 0 from small r. But here, see what will be the integral of dA? dA will be E times 4 pi r square. That is no doubt. But here, the dV won't be 4 by 3 small r cube, because we want the volume, like we need to consider the volume only where the charge is present. So here the volume will be pi capital R cube by epsilon naught. So 4 pi gets cancelled. From here we say that electric field is equals to rho r cube by 3 epsilon naught small r square. So if we try to draw a graph for this electric field, this is electric field, here is r distance. See, till x equal to r, it is a straight line of slope rho by 3 epsilon naught, and after that okay, so this is the graph. See, we have to be very careful when we are doing anything. Like this may be a question in any year of JEE, because like JEE basically requires us to solve questions. Like they ask us questions which come after a very long time of work. So we have worked out this much all, and after that, finding the slope is a very small thing, but still to reach that we have to do a lot of stuff. So we have to be very careful while doing things, and we have to catch small things also. This is the electric field here. Now let us solve one more. Let us try to plot the electric field inside another type of a conductor. See, this is an infinite charge sheet of infinitely long. Okay, which has again rho as the volume charge density. Let this be the center. Okay, so we are asked to find out the electric field at a distance x. So now, when there was a spherical charge, we consider our Gaussian surface to be a sphere. Now since here we have a symmetry along this way and not this direction, so we consider a Gaussian surface in a similar manner. See, we consider a cylinder here of length 2x and surface area S. So now, what is the net flux through this sphere? See, basically the electric field won't be in this direction since it is infinitely long. The electric field is in only this direction, right? So the net flux here is 2 times ES. Now why is this 2? See, flux is going out from here, flux is going out from here. Electric field in this direction also, this direction also, right? So 2 times. And due to this surface it becomes 0. So the net flux is equal to 2 times E into S. Now what is the charge enclosed? Charge enclosed is rho times, what is the volume? Volume is equal to S into 2x. So if we solve this, we get E is equals to rho times x. Okay. Sorry, by epsilon naught is also there. Yeah, so here it is rho x by epsilon naught. Now consider we need to find the same thing at a distance y outside. Let this be L and this be L. So we need to find the flux, electric field at a distance outside. So again now we consider another cylinder of length 2y. In that case, still the electric flux is, the net flux is equal to 2Es, but the charge enclosed is equals to 2 times rho S into 2L, because now the charge enclosed is only still here by epsilon naught. Again 2S gets cancelled, so electric field is equal to rho L by epsilon naught. note that it does not depend on the place where like it does not depend on y. Instead, the electric field is rho L by epsilon naught. So these are a few more applications of Gauss law where we find out the electric field due to conductors, charge bodies in fact. Now let me go to the cavity thing. See, consider a charge body with let this be the center. Now what I do is I remove this is a sphere, okay. Now I remove one other sphere from this. Basically I make a cavity. The cavity does not mean that I remove some part of the actual sphere. The cavity simply means that there is no charge present in that area. Let this be O. Let this center be O dash. Okay. So what we are going to find out now is we are going to find out the electric field at a point inside the cavity which has the position vector of r from the bigger one and y vector from the smaller one. So one may visualize, see, because superposition principles work well in the what we say electrostatics, one may say that the cavity arises in this way. See here, the volume charge density is rho. This is O. Now I want to make a cavity here with center O dash. So it is similar to superposing a negative charge sphere in this. If the volume charge density here is rho, then the volume charge density here should be minus rho. Thus by superposition, the charge here becomes neutral and there is no net charge present inside this particular area. So by superposition we can say that. Now what do we want is, we want to find out the electric field at this point, which has y vector from here and r vector from here. So see, so yes. So what is the net electric field present there would be equal to electric field due to full positive plus electric, see I am writing vectors, that's why I am adding here, okay, electric field due to full negative. Then it would superimpose and give us the net electric field due to this configuration, right? So what is the electric field net here is equal to what is due to full positive. Just now we have found out that the electric field due to the full positive will be E r vector by 3 epsilon naught. See, I don't care about the direction right now because since I am writing those vectors, okay, plus what is electric field due to full negative, this will be equal to, see, minus rho, because this is negative, times y vector by 3 epsilon naught, which is equal to rho by 3 epsilon naught times r vector minus y vector, right? Now just observe this part, this triangle. Due to the parallelogram law, we know that O dash vector plus y vector is equal to r vector, right? So from here we say that O dash vector is equal to r vector minus y vector. So it is, this will turn out to be okay. So just hoping, like assuming that it's clear, So the electric field, let this point be P. Electric field at a point P inside the cavity is equal to rho by 3 epsilon naught times O dash vector. Now see, rho is constant, 3 is constant, epsilon naught is constant, O dash vector is also constant. See, whatever may be the point, O dash vector will be this much. Its magnitude is fixed and its direction is fixed. So this is a constant value. So what we conclude? We say that the electric field inside this cavity is constant and is in this way. Like its direction is so the electric field inside this cavity is constant, okay? Right. Now further you will learn that basically this is just a formula to be noted down right now. Electric field is equals to minus dV by dx. Now since electric field is constant, so we can also comment on the potential, which we will be discussing later on. Now in the same terms in which we have done this thing, we can similarly do that for a cylindrical thing also. Now let us move forward for to learn the concept of conductors. See, what is a conductor? We know that every metal is a conductor, but what does its properties actually include of? See, for the conductors, we have infinite number of free electrons. Okay, so the conductor has infinite number of free electrons which can conduct the flow of charge. So first point, okay. Now if what happens, see, whenever there is charge, okay, like they have free electrons, but suppose that this is a neutral conductor and somehow I give it a charge, some positive, some Q, okay. So what happens is, this charge, suppose it is positive, so it occurs on the surface and no charge is present inside the, between the metal, and it's not necessary that the charge is uniformly distributed. Any excess charge, it may be positive or negative, moves to the surface. See, now why is it so? Suppose it is because to maximize the distance between them. Now we know that the electrostatic force is inversely proportional to the distance square. So if suppose the charge is not here and somewhere here, the field acting, due to the force acting between them, they have a tendency to move forward, and thus ultimately finally this configuration occurs where we have the whole charge at the surface and not inside the metal or a conductor. The third point is the electric field inside the conductor is 0. This is obvious, see, because see, we consider a Gaussian surface anywhere, anything. So it would turn out simply that since there is no charge enclosed inside, so the electric field would be 0. Okay. then the most important final one, the like inside the conductor the potential of every point is same. So these are a few properties about the conductors. Remember that electrostatics is like a question. If there is a question from electrostatics, it is most likely meant to be from the chapter of conductors. Such important is this chapter. Such important is this topic. So let me illustrate a few questions on conductors. Suppose, see, this is a like spherical conductor with a hollow space inside. Okay, the space inside is hollow, and it has the conductor has a net charge plus Q. Net charge of Q. Okay. Now also like in this hollow space there is also a charge Q, small q. So what we are required to find out is the charge appearing inside the conductor, in the inner surface of the conductor, and the charge appearing in the outer surface of the conductor. See, because we know that there will be no charge here, all the charge will be going to the surface. Now we need to find out how much charge comes to the inner surface and how much charge goes to the outer surface. So for finding out, see, what do we do? Basically, we take a Gaussian surface here. We know that the electric field inside the conductor is 0, so the net flux should be 0. Thus, the total amount of charge enclosed inside that Gaussian surface should be 0. Why? See, because simply electric field is 0, implies net flux is 0, which implies Q enclosed is 0. Now what is Q enclosed? Let this be Q inner. So Q enclosed is Q inner plus Q. Thus Q on inner surface is equal to minus Q. Right? Now we know that there exists something called of conservation of charges. Thus the net charge on the conductor should still remain capital Q. Thus we say that Q inner plus Q outer is equals to capital Q. And what is Q inner? Q inner is minus Q plus Q outer. So Q outer is equals to Q plus Q. So this is finally it would have a negative charge of minus Q here and at the outer surface Q plus Q. So a few techniques about solving this question. Instead of doing every time this thing, see, whenever we find a charge, okay, the face towards the charge should have the same magnitude of the charge with the direction sign opposite. Suppose if I had negative Q here, then it would be positive, okay, and thus there exists the conservation thing, that it would become Q minus Q. So this applies to many configurations. So just illustrating on what I said right now, let us solve one more question. See, the question says that there are concentric, spherical conductors. This is spherical concentric hollow conductor, okay. Having charges in such a way that inside is minus 2Q, this is neutral having 0 charge, and then this has positive 2Q and this has minus 3Q. So now we are asked to find out the charges at all the surfaces. See, this is a thin spherical what is a conductor, but still, like if you see it microscopically, it will be having some thickness, but we do not mention it here. So every conductor still has two faces, so we need to find 1, 2, 3, 4, 5, 6 the charge distribution at all these faces. Now through whatever I said just now, suppose this part has minus 2q, then this surface, the inner surface, should have the same magnitude with a positive sign, right or not? Because see, consider 1, the conductor 1, let this be in this way. If I consider a Gaussian surface inside, the electric field should be 0, inner charge, the sum of inner charge should be 0. We already have minus 2q here, so there should be plus 2q this side. Only and only then it will become 0, right? Now, see, this conductor was neutral and all. Plus 2q charge came here, so this surface should get a minus 2q charge, right? Thus, this surface, I'll write them here. So we get, see, q11 is equal to plus 2q, q12 is equal to minus 2q. Why was it so? To have charge conservation. Now, this phase has minus 2q, so the exactly opposite phase to it should have the same magnitude of charge with a direction, like sign positive, say opposite sign. So the third surface would have plus 2q, and now apply the conservation thing. The thing has, on a whole it has plus 2q charge, and the whole of 2q charge comes to the third surface. So what will fourth surface have? Fourth surface will have 0 charge. Okay. Now if this is 0, the opposite thing should also have 0. Okay. Now if this is 0, the whole of the charge should occur on the opposite side, right? Like to the extreme end. So Q6 will be 0. Sorry, Q6 will be minus 3Q. Now in this configuration, after a long time, this will be the positioning of all the charges, so that like all the characteristics of metals are seen into. So now I'll tell you one more thing. Like instead of going this way, we can also say that, see, whatever is the net charge present over here, that net charge straight away goes to the opposite side. So suppose if this were plus 4q, then what is the net charge? We have net charge of minus 2q. So we can, so this was the earlier configuration, okay. Now the net charge present on all the 4 is minus 2q, right? Is it minus 2q? No, it's minus q. So we say that the minus q charge comes here. If it is minus q, the inner should be minus 2q. If it is minus 2q, it should be plus 2q. If it is plus 2q, this should be plus 2q. Since this is plus 2q, it should be minus 2q, and this becomes plus 2q. See, even in this way, all the properties are matching, like all the properties remain the same. So, like this is the way we need to solve any question related to concentric spherical conductors. Now there is one more concept of like parallel, like plate conductors. Suppose this plate has a charge of Q. So what should happen to the charge distribution? We still said that the charge will go to the surfaces, right? So what happens here is, consider this point. Let this part has a surface charge, surface charge density of sigma. This is infinite. No, not infinite actually. Yeah, okay. So this has sigma, and let this also, this has sigma dash. So what is the electric field at this point? We have seen that due to the plate, the electric field here would be in this direction, sigma by 2 epsilon naught, and due to this it will be in this direction, sigma dash by 2 epsilon naught. For the electric field at this point to be 0, sigma should be equal to sigma dash, and which means that Q at left surface, it should be equal to Q at right. Also q left plus q right is equal to q. So q left is equals to q right is equals to q by 2. So if given charge q, it will distribute it in such a way that they come here and here, and thus the electric field inside becomes 0. Now in similar ways, let us try to solve this thing. There are two plate conductors. This has 2q charge, this has 4q charge. Okay. So what is the configuration? One may say that, see, since it is 2q, put q here, 2q and 2q here. So, but this is not the case. See, if we put q and q, the electric field inside due to this and this will become 0. But due to this and this, it will be in this direction, and still it will be in this direction, so the net field does not become 0. So in this case, the best technique is, again, see, calculate the net charge. Now what is the net charge? The first and foremost procedure is, take a, assume that here it is 2q dash, then it would be 2q minus q dash here, and see, the opposite thing should be, what do you say, the charges here and here should be opposite, so it will become minus q dash, and thus it will become 4q plus q dash, right? Now take any point and then find out the electric field. That would lead us to an answer. But instead of doing all this, I'll tell you a technique which we can use and find out the answer. Let us say we'll have this q dash here itself. Okay, what I say is, see, add the total charges. So what is equal to 6q? Then divide by 2 and give them at both ends. Now conserve the charges. Since it was 2q, let it be minus q. Since it is 3q, let it be q. Now put q dash is equal to minus q. You will see that everything gets satisfied. So this is the distribution of charges happening. So what did we do? We basically added the charges, then divided it by 2 and put it somewhere else. Now in similar backgrounds, apply the same concept here. (2q, 3q, minus 5q). So what is the net sum? Net sum is 0. So 0 by 2 is 0. We have 0, 0 here, 2q here, so minus 2q here, minus 2q here, so 5q here, and minus 5q here. So everything is satisfied. Okay. So this is a simple way to solve this thing.